Again, not in slope-intercept form. Again, I'm going to graph using intercepts. If I let x equal 0, goodbye to that part, I have negative 4y less than 4. Dividing by negative 4 gives me a y value of negative 1 if that had been an equation. If I let y be 0, that zeroes out the 4y term. All I have is x equals 4 there, and that gives us a second point on the graph. So 0, negative 1 is 1 unit below the origin. 4, 0 is 4 units to the right of the origin. Looking back at the problem, there's no equal to, which means this is going to be a dotted line boundary, which we're going to graph, dotted or dashed. And we don't know whether to shade up or down, above or below this line. I'm going to try the origin as a test point. When I substitute the origin in for both x and y up in the problem up top there, I find that the left side zeroes out. 0 less than 4 is a true statement, and so 0, 0, the origin is part of the solution set, and so we're shading above. Notice there was a less than in the problem, but we were shading above. That's because I told you that rule only was in effect when the problem was given to us in slope-intercept form. Notice if we were to subtract that x to both sides, we'd have negative 4y less than negative x plus 4. And in the process of dividing each side by a negative, we'd be changing the direction of the inequality, giving us positive 1/4 x minus 1, which is what I have graphed. There's my y-intercept of negative 1, and up 1 over 4 takes me to that next point. And it was that act of dividing through by negative 4 that changed the direction of the inequality. Okay, last couple of problems here. Now we have a system of inequalities. We have two of these to graph at the same time. The first graph has a y-intercept of 2, has a slope of negative 1/2, so down 1 and over 2. This is missing the equal sign, so this will be a dashed line graph. I'm going to do the best I can to draw a straight line here. Okay, that is in slope-intercept form, so the less than means shade below. I'm going to either mentally remember shade below, maybe draw a couple arrows there to remind myself. The second inequality has a y-intercept of negative 3, and the slope there is 1. There's an understood 1 in front of the x, so up 1 over 1. And we'll have another dotted line boundary for our graph. This one's a greater than, meaning shade above. Now when we have two equations we're graphing, we want to know where do the lines cross. In other words, what is the xy point that's on one line and on the other? And that word and is important because here we're trying to find what set of points satisfy one inequality and the other, and it turns out that it's this triangular region over there on the left. So we shade that region. The stuff that only had shading once, or that was only partially working for one inequality but not the other, is not part of our total solution set. In this last problem, number 6, we have 3 inequalities. The first one has a y-intercept of 2. There we go. Its slope is negative 1, so down 1 over 1. And again, this is going to be a dotted line boundary that I'm about to draw in. Y less than 4 is going to be a horizontal line, y equals 0x, a slope of 0 plus 4. Right now, if we were to look at the shaded regions, we'd be shading above the diagonal line, we'd be shading below the horizontal line, so we'd be over here in the right side of the graph where I'm pointing. X greater than 1 is not a diagonal line. X equals 1 is a vertical line. This is the only time we do not shade above or below. You can't really shade above something that's vertical. So the left side, right side argument takes over, just as if we were on a number line. If this were a number line, we'd have an open circle at 1, shade to the right. We're going to do the same thing, shading to the right. And we're going to have this weird shaped region over here on the right, which we're going to shade in as our solution set for this problem. Notice the dotted line boundaries on all sides.